A study reported in 2010 in the journal Archive of Sexual Behavior looked at sexual practices in healthy European, American, Asian, and Hispanic female populations. A portion of the research looked at the age of sexual debut, the age that women first engaged in intercourse, for women in the three study populations mentioned above, European, American, Asian, and Hispanic. It says an ANOVA completely randomized design was conducted using SPSS to determine if there was a difference in the age of sexual debut among the three groups of women. The results are reported below. Based on the results below, does there appear to be a significant difference between the groups of women? Based on the results of the ANOVA procedure below, what, if any, multiple comparison procedures should be conducted on the data? Okay, so the first thing they ask is, does there appear to be a significant difference between the two groups of data? To answer that, we simply have to look at the test stat, which led to a p-value, a significance level. Now, this is done in a software package called SPSS, which is really popular, and it does all the work for you. Once you enter the data in the SPSS software, will do all the crunching of the numbers and produce these values. They'll produce the test stat F, and they'll produce a p-value. Now, you could go to the table and get a critical value and compare it, but you really don't want to do that if the computer has already given you a significance level. A significance level here is a p-value, in other words. They're saying this is the observed significance level. And what you're going to do with that is you're going to compare it against alpha. Now, in this problem, they didn't give us an alpha, but we can compare it against what we would think to be a reasonable alpha. Usually we choose 5% for that. But, think about it. You never see alphas higher than, say, 10%. And even if you went radical and chose an alpha of 20%, this p-value is much larger than that even. So the p-value here is actually 0.364. If we compare that against kind of the default alpha level, which is 0.05, there's no doubt that the p-value is larger, right? This is 36%, this is 5%. Because it's larger, that means you do not reject the null hypothesis. Now, what does the null hypothesis say? Well, for these completely randomized design experiments, it says they're all the same. So it says what? Basically that the average age for a European American woman to first engage in intercourse, the average age for Asian women to first engage in intercourse, and the average age for Hispanic women is going to be essentially equal. If you say you do not reject HO, you're saying that this is okay, the idea that all the means are equal. And if they're all equal, then we basically have no need to do a multiple comparison procedure on the data, because what is it going to say if I compare these separately to each other? Well, if I'm already saying they're all the same, and if I compare them separately, it'll just confirm that they're all the same. So there's no need to bother even look at that. So what multiple comparison procedure should be used? None, because essentially we were unable to reject the null hypothesis. So you just want to say, do not use a multiple comparison procedure here. It doesn't serve any benefit to do so. It would be a waste of your time, essentially. And the reason why is because we did not reject the null hypothesis. So please remember that in order to use a multiple comparison procedure, you should first reject the null hypothesis. If you don't do that, don't waste your time. If you are unable to reject, there's no need to do a multiple comparison procedure. So the idea should be, we must reject first, and then if we reject, then we can go ahead and use the multiple comparison procedure. And that's it.